Welcome to Brain Vision.
Okay, so in this question, we have um, a vibrating piece of metal that's attached to a string, um, and then that string is hung over a pulley, and at the end of the string, there is a mass attached to it. So here is our piece of metal, and then here is the vibrating string. The string has a standing wave pattern, and then there is a pulley here, and then there is a mass of capital M at the bottom. So in its initial state, it is the little vibrating metal piece is creating a standing wave pattern with two antinodes um, in the horizontal part of the string, and the mass is straight down um, from where it's hanging at the pulley. But then the frequency is held constant with the vibrating metal piece. And then a wind blows on the mass and moves it towards the right. And when this happens, the standing wave pattern changes to just one antinode on the horizontal part. And then the mass is blown over to the right here and has a wind applied to it here. So we're just going to call the force of the wind F. And we're supposed to figure out how the magnitude of this wind force that is required to make this situation happen, to go from two antinodes to one antinode. So the thing that we should pay attention to here is we're only allowed to use the variable m in our answer. It's a symbolic problem, so we don't have, we don't have a final numerical value, but we can use capital M, and that's it. The other thing is we should pay attention to other important values, like the frequency is constant, the linear mass density of the string mu is going to be constant, obviously, and the length of the string that's vibrating is constant. So, so we're supposed to figure out how strong this force F is in terms of M. So the way that we can do that is first we should start by analyzing what these frequencies should be in terms of other values. And then we can set these frequencies to each other because we know that the frequency is constant, so they will be equal, and then we can use that to help figure out what our tension is in the string is, which we can then later use to figure out how strong the force of the wind is. So what we're going to do is I'm going to call this situation, 2, because there's two antinodes. So, F2 makes more sense there. And we'll call this situation 1, since there's only one antinode. So for F2, the frequency when there's two antinodes, so F2 is going to be equal to V2 over lambda 2. V2 is going to be the tension in the string in this situation. So T2, and then lambda, or it's going to be V2 is going to be related to the tension and the mu value. Mu is constant, so only tension changes. And then lambda is going to be related to the length of the string. Since we have two antinodes, lambda is going to be equal to L. So the formula for lambda in all situations here is going to be lambda is going to be equal to 2L divided by N. So for F2, since lambda is 2L divided by N equals 2, lambda 2 is just equal to L. So for our first part of this equation, we can write 1 over L, and then our expression for the speed of the wave is going to be the square root of T2 over mu. Then for F1, which we can go ahead and set these equal now, because we know that the frequency is going to be constant. So then our F1 would be equal to the speed of the wave in this situation, V1 over lambda 1. In this case, since n is equal to 1, lambda is then equal to 2L. So then our first part of this equation becomes 1 over 2L, and then our speed of the wave is the square root of t1 over mu. And so since we're concerned about the tension in the string in the situation where there's only one antinode, we want to solve this equation for t1. So I'm going to go ahead and rewrite this first so that we can get rid of a bunch of unnecessary information. We only need 1 over L times the square root of t2 over mu is equal to 1 over 2L times the square root of t1 over mu. And then we can do some algebra to solve for t1. So both sides have an L in the denominator and a square root of mu in the denominator. So we can go ahead and get rid of those. And then we're left with the square root of t2 equal to 1/2 t1, the square root of t1. And if we solve this for t1, we will get 4 t2 is equal to t1. And we just multiplied both sides by 2 and then squared both sides. And so that's a very helpful relation. So what we have to do now is we need to figure out an expression for t2, and then we have to find a way of relating t1 to the force of the wind. So what we do for this part of the solution is we need to do some force diagrams on the box. So in situation 2, where we had 2 antinodes, we just had, the box was just hanging vertically from the pulley, so we just had 2 forces on it. We had T2, the tension in the string, and then we had the weight of the box, mg. So we can say that T2 is equal to mg. So then we know that T1 is going to be equal to 4 mg. And that's really important to know for later. Then, in situation 1, we have 3 forces acting on the box because now the wind is blowing on it. So we have the wind blowing to the right, and we have mg pulling down on it again. But now T1 is pulling up at an angle. And we know that the magnitude of T1 is equal to 4 mg. But we also know that the box is at rest in this situation. Because we're able to have like a standing wave on the horizontal part of the string, so the box has to be at rest. If it was moving around, we wouldn't have a stable standing wave. Which means that the y component of the of T1, so T1y, has to be equal to mg, and then T1x, the horizontal component, has to be equal to f. Which is really great because now we know what both components are equal to, and we know the value of the full T1 vector, so we can use that to solve for f. So we can say that, using the Pythagorean theorem, we can say that T1 squared is equal to T1y squared plus T1x squared. And then if we solve for T1x, we get T1x is equal to the square root of T1 squared minus T1y squared. We know that T1y is just mg, and we know that T1 is 4 mg, and we know that T1x is equal to f. So we can say that f is equal to the square root of 4 mg squared minus mg squared, which is f is equal to 16 mg squared minus mg squared, which is just the square root of 15 mg squared. And so we can say that f is going to be equal to the square root of 15 m, and then we can pull the mg out of the square root. So our answer is the square root of 15 mg. And that's how you do this problem.